Hello everyone, I am Bireshwar Roy. I am currently pursuing my 4th year PhD in the Department of Physics, Indian Institute of Science, Bangalore. In this NPTEL GATE Physics course, I will be discussing some previous year's GATE Physics questions and try to solve them with proper explanations. This question was asked in the GATE Physics paper 2020. This is a MCQ type question having 1 mark. The topic of the question is electromagnetic theory. The question is a medium with relative permittivity or dielectric constant epsilon r greater than 1, relative permeability mu r equals to 1 and conductivity sigma greater than 0 is semi-transparent to an electromagnetic wave when option A, conduction current is very greater than displacement current. Option B, conduction current is very less than displacement current. Option C, conduction current equals to displacement current. And the last option, option D, both conduction current and displacement current are 0. So let us see how to solve this problem. For a linear, homogeneous and isotropic conducting media, the Maxwell's equation can be written as curl of H vector equals to JC vector plus JD vector. So this is also known as modified Ampere's law. In this equation, the H vector is the magnetic field intensity vector, JC vector is the conduction current density, and JD vector is the displacement current density. Now, the conduction current density JC vector is given by sigma times E vector. Here sigma is the conductivity of the media and E vector is the electric field vector. And the displacement current density JD vector is given by del D del T. Here D vector is the displacement vector. Now this is also given by epsilon times del E del T. Here epsilon is the permittivity of that medium. Now if we consider a plane wave or monochromatic wave solution for the electric field, then it can be written as E vector as a function of r vector comma time, that is t, equals to E naught vector times e to the power I k dot r minus omega t. Here E naught is the amplitude of the electric field and k vector is the wave vector for that electric field. Now the conduction current density Jc is given by sigma times E vector. Now we'll put this E vector expression in this equation. So we'll get Jc vector equals to sigma times E naught vector times exponential of I times k dot r minus omega t. And the displacement current density vector will be given by epsilon times del E del t. So we'll put the expression for E vector in this partial derivatives and we'll get epsilon times minus I omega times E naught vector times exponential of I k dot r minus omega t. Now E naught vector times exponential of I k dot r minus omega t is our actual electric field vector. So we can write it as JD vector equals to minus I omega times epsilon E vector. Now we'll take the ratio of the magnitude of the conduction current density vector, that is JC vector, and the displacement current density vector, that is JD vector. So it can be written as mod of JC vector divided by mod of JD vector equals to mod of sigma E vector divided by mod of minus I omega epsilon E vector. So we'll get effectively sigma by omega epsilon. Now as we are given the medium as semi-transparent medium, for that we have the condition that sigma by omega epsilon is very less than 1. This actually implies that the medium is the poor conductor or lossy dielectric. Now, if we implement this condition in the expression of the ratio of JC vector and JD vector, then we will get mod of JC vector divided by mod of JD vector equals to sigma by omega epsilon, which is very less than 1. So this implies that mod of JC vector is very less than mod of JD vector. So we can conclude conduction current for in this media is very less than displacement current, which is option B is given in the question. So according to our solution, a medium is semi-transparent to an electromagnetic wave when the answer is option B, that is conduction current is very less than displacement current. This question was asked in the GATE Physics paper 2020. This is a numerical answer type question having 1 mark. The topic of the question is electromagnetic theory. The question is, far from the Earth's magnetic field can be approximated as due to a bar magnet of magnetic pole strength 4 into 10 to the power 14 ampere meter. Assume this magnetic field is generated by a current carrying loop encircling the magnetic equator. The current required to do so is about 4 into 10 to the power n ampere, where n is an integer. So the value of the n is, so we have to find the value of n here. One information is given in this question is Earth's circumference is 4 into 10 to the power 7 meter. Now let us see how to solve this problem. Far from the Earth's magnetic field can be approximated as due to a bar magnet of magnetic pole strength P equals to 4 times 10 to the power 14 ampere meter. Now we can assume that this Earth's magnetic field is generated by a current carrying loop encircling the Earth's magnetic equator. So the current carrying loop has the radius A, which is the radius of Earth, and the magnetic dipole is directing towards the north direction. The magnetic dipole moment is mu, and the length of the magnetic dipole is 2a. So magnetic dipole moment mu vector of the bar magnet of Earth is given by mu equals to p times 2a. So this is the relation between the magnetic dipole moment with the magnetic pole strength. Here a is the radius of Earth. Now assume that this magnetic field is generated by a current carrying loop encircling the magnetic equator. So in the diagram we can see there is a current carrying loop encircling the magnetic equator of the Earth having radius small a, which is the Earth's radius, and the passing current is I, and due to this current magnetic field will be generated and the corresponding magnetic dipole moment is mu vector, which is directing towards the north direction. The current required to do so is about 4 into 10 to the power n ampere, that is given in the question. So our current I equals to 4 into 10 to the power n ampere. We have to basically find this n value. Now we know magnetic dipole moment due to a current carrying loop having radius small a is given by mu equals to I times pi a square. Now we will compare the equation 1 and equation 2. So equation 1 was magnetic dipole moment is equals to P times 2a, where P is the magnetic pole strength, and also for the current carrying loop the magnetic dipole moment is I times pi a square. So we'll equate that two equations. So we'll get P multiplied with 2a equals to I times pi a square. So from here we can get I equals to P times 2a divided by pi a square. So this will give I equals to 2p divided by pi a. Now in the question it is given that the magnetic pole strength P equals to 4 times 10 to the power 14 ampere meter. The current is 4 into 10 to the power n. Earth's circumference, that is 2 pi a, is 4 times 10 to the power 7 meter. So we'll use this information in this equation. So we'll get 4 into 10 to the power n equals to 2 times 4 times 10 to the power 14 divided by 2 times 10 to the power 7. So here 2 and 2 will be cancelled out from the numerator and denominator, and from the left side and right hand side the 4 will be cancelled out. So effectively we will get 10 to the power n equals to 10 to the power 7. So the value of n is 7 for this question. We can also solve this problem in an alternative manner. The definition of the pole strength is given by P equals to surface integral of H vector dot ds vector. So we are considering the Earth's magnetic field is due to a current carrying loop having radius small a. So for that current carrying loop, the H field is given by I by 2a along the z cap direction. So here it will be along the north direction. So from the definition of pole strength we can write P equals to H times area of the loop, that is I by 2a times pi a square. So it will give the pole strength P equals to I times pi a divided by 2. We can write it as I by 4 times 2 pi a. So here 2 pi a is the circumference of the Earth. So we'll put the value of P here, that is 4 into 10 to the power 14, and I value is given in the question 4 into 10 to the power n divided by 4 times 2 pi a, that is circumference of the Earth, that is 4 times 10 to the power 7. So if we just cancel out the 4 and 4 from the left hand side and right hand side, and from the numerator denominator the 4 will be cancelled out. So effectively we will get 10 to the power n equals to 10 to the power 7. So by comparing we can get n equals to 7. We solved this problem using two different methods, and from the solution we found that the current required to do so is about 4 into 10 to the power 7 ampere, where n is the integer. So our n value is 7 for this question. This question is from the GATE Physics paper 2020. This is a NAT, that is numerical answer type question, having 1 mark. The topic of the question is solid state physics. Specifically, this question was asked from the chapter crystal structure. So in the question, a two-dimensional lattice structure is given. The question is the number of distinct ways the primitive unit cell can be constructed for this two-dimensional lattice as shown in the figure is. So we have to find how many ways we can construct the primitive unit cell with this two-dimensional lattice structure. We know primitive unit cell is the smallest volume cell possible in the lattice structure. So primitive unit cell is the building block of that lattice structure. All the lattice points belonging to a primitive cell lie at its corner. Therefore, the effective number of the lattice points in a primitive unit cell is 1. Let us see the number of distinct ways of the constructing the primitive unit cell for two-dimensional lattice structure. So, according to the definition of primitive unit cell, the lattice points lies at the corner of the primitive unit cell. So, now we'll see how can we connect the 4 lattice points in this two-dimensional lattice structure in different manners to form the primitive unit cell. Possibility 1 is by connecting these 4 points we can get a primitive unit cell for this two-dimensional lattice structure. So, this is number 1 possibility. Number 2 possibility is this. So, connecting these 4 points we can get another primitive unit cell for this two-dimensional crystal structure. Third possibility is this. So, connecting these 4 points we will get the third possible primitive unit cell. Fourth possibility is again an parallelogram connecting by these 4 points. And the last and fifth possibility is connecting these 4 points to get the parallelogram shaped primitive unit cell for this two-dimensional crystal structure. So, there are total 5 possibilities. So, number of primitive unit cell in 2 dimension is 5. From this solution, we found that for this two-dimensional lattice structure, the number of distinct ways the primitive unit cell can be constructed is 5.